taking two angles and you're trying to add two angles together, the cosine of two angles, or subtract the cosine of two angles. Same thing with the sine and cosine, the sine and the tangent. So there are 6 in this box because you have 1 for each addition, subtraction, trig function. The thing to notice is that you're not just simply distributing. So this isn't the distributive property like it would be in algebra. So it's not like you have an x outside and then you're distributing like an a and a b, where you're like distributing that through. Because this is a function, it's a trig function, and it's not a variable. So we're not simply just distributing. So when you see it in your book, don't be like, oh, I'm just going to distribute the cosine through, because it's not a variable, it's a function. So a variable we can distribute through, but that's a trig function that has an actual value with an angle that goes along with it. So that's why these formulas are here, so that you don't just distribute and you attach it to a formula. The first 2 problems, one deals with a degree, because I think it's a little easier to start with a degree, and then the one next to it kind of goes along with a radian to see how a radian works. So it says to find the exact value of the sine of 75 degrees. So besides just plugging that in the calculator and getting a value, we want to go beyond that and see if we can find the exact value using what we know from the unit circle. So we have to use things we already know from the unit circle in order to help us find something that we don't know in the unit circle. So the first goal would be to look at the angle and try and get 2 values from the unit circle that would either add or subtract to be 75 degrees, and it's up to you. So you've got a choice. You can get 2 angles to add to be 75 or 2 angles to subtract. So Anna, can you give me 2 angles that would make 75 degrees? That are on the unit circle. So think of an angle that's on the unit circle, 2 of them combined to be 75.
45 and 30.
Yeah, so if I have 45 degrees and 30 degrees, they add to be 75 degrees. Both of those angles are on the unit circle, and we can find values for them because we know those values from the unit circle. So we want to find the sine of these 2 angles, 45 degrees and 30 degrees. If I find the sine of the sum of those angles, then I can get an exact value for the sine of 75 degrees, because those 2 angles together would give us the 75 degrees. So this is a plug and chug formula. You have a formula, just like the quadratic formula, it's plug and chug. You plug in numbers, you chug through the problem. So you're going to go to the sine formula, which you will have it memorized. You'll use it enough that it will not be that bad memorizing it. But it says you're taking the sine of the first angle, that's what A means, alpha, times the cosine of the second angle, or beta. And then you're adding that to the sine of the second angle times the cosine of the first, so that we have both angles that we're looking at. So your first angle would be the 45 degrees, the second angle is the 30 degrees. So we're taking the sine of the first angle times the cosine of the second angle. And then you're adding that with the sine of the second angle times the cosine of the first. So that's what the formula says. So I'm just taking the formula, plugging the 2 angles in. And then you go to the unit circle, and you think about the sine of 45 degrees on the unit circle. So Jordan, what's the sine of 45 degrees on the unit circle? Square root of 2 over 2. And the cosine of 30 degrees is? What'd you say? The other one. Square root of 3 over 2. So the sine of 45 degrees is the square root of 2 over 2. The cosine of 30 is the square root of 3 over 2. And then you're adding that to the sine of 30. That's where my 1/2 is. And the cosine of 45 is also the square root of 2 over 2. So we're using stuff that we know from the unit circle, and we're applying it to a formula to see if we can get an exact answer. And then you multiply. So I'm multiplying these 2 together. They're both square roots. You can multiply them. So we have the square root of 6 over 4. You multiply the top, you multiply the bottom. When you're multiplying fractions, top times top, bottom times bottom. And then if I multiply the other top, I have the square root of 2 over 4. And then the last thing that we can do to kind of simplify this, these both have a 4 in common. So we could pull out the 1/4 and separate it from the radicals, because the 1/4 is a whole number. So these really have a 1/4 in common. I'm just pulling that out and letting the radicals kind of be in the back. Now I know that you're telling me right now, you're not telling me, but you're thinking, this really doesn't make a big difference to you because it's not an exact number and it's kind of hard to say, all right, well, what the heck value is that? However, that is an exact answer that you wouldn't need to use a calculator for, and there really wasn't technology back when the Greeks created the unit circle. So the sine of 75 degrees is 1/4 times the root 6 plus root 2. You can put it in your calculator and get a decimal answer that actually is not exact because it's rounded at some point. Questions? So we're going to try and do the same exact thing, but we're going to try and do it with a radian value instead of a degree value. But our end goal would be to try and find two angles that would combine to be pi over 12. So I would first suggest thinking about angles with common denominators. So how could I take something over 12 plus something over 12 to get a pi over 12? So our goal is to get 1 pi over 12. Or how could I subtract two things to get pi over 12? So when you're dealing with a fraction, I would think more like with the common denominators, and then we'll reduce those. So what numbers could I put on the top of this that would subtract to be 1 or add to be 1? Probably subtract is the way you're going to want to go. Natalie, what do you think? What numbers could we use on the top?
Would you be able to use like the pi over 3 and pi over 4 and then multiply them? So then it'd be the 3 pi, or it'd be 4 pi over 12 minus 3 pi over 12.
Good, there you go. So she said 4 pi over 12 minus 3 pi over 12. 4 minus 3 gives me 1. Natalie, 4 pi over 12 is really
Pi over 3.
pi over 3. And 3 pi over 12 is
Pi over 4.
pi over 4. So those are two angles on the unit circle. And as a common denominator, they would subtract to give us 1 pi over 12. So the 4 minus 3 gives us the 1. So see if you can apply those to the cosine, the difference formula for cosine, and see if we can get an exact value for the cosine of pi over 12. Both of these formulas use the distance formula. We talked about the distance formula at the beginning of the year. You used a lot in geometry. So the sum and difference formulas were created from the distance formula from geometry. So yeah, kind of using the distance, like a point is on the unit circle, and it creates a triangle. So it does use the distance formula, something that you have seen. So if you want to look at that proof, like you have used the distance formula, so it would make a little sense to kind of just look at it. So, Maddie, what is the cosine of pi over 3?
Cosine of pi over 3 is 1.
And the cosine of pi over 4?
Square root of 2 over 2.
And the sine of pi over 3?
Square root of 3 over 2.
And then the sine of pi over 4.
Square root of 2 over 2.
Perfect. So all we did was we took the, I'm just using the sum. It should be addition here. you all used addition. Took the difference formula, you're plugging the numbers in, and then if you multiply them together, you end up with the square root of 2 over 4, the square root of 6 over 4, and then we can do the exact same thing we did to the other one. Pull out the 1/4, and you end up with the square root of 2 plus the square root of 6. Does anybody know what is special about the angles that we have up here? 75 degrees, pi over 12. We learned about these angles. They're on that sheet too. What do you think pi over 12 would be as a degrees? Just taking a shot at it. Noticing that these angles give us equal solutions. They add to be 90 degrees. So when your values are the same, those are called cofunctions. When I have the sine of 75 degrees, the cosine of 25 degrees, those are cofunctions. So if they add to be 90 degrees and you're taking the sine and cosine of those angles, they should be equal. So that's why the values are equal here, because pi over 12 is actually 25 degrees. And we have the sine of 75 degrees. So that's why they are equal. Yeah.
Why are we adding them? Because would it, like, when we got the two angles at first, like before pi over 12?
I didn't mean to add them here. Still should be subtracted. They need to be added in the formula. Thank you. So they should be added in the formula because the formula actually does the opposite, and that's because of the difference formula. Other questions? So that's one application of the sum and the difference. There are also two other applications that we're going to look at. But one thing that the sum and difference formula does would be to give us exact values that you wouldn't necessarily have memorized on the unit circle. So you probably don't have the cosine of pi over 12 memorized. Questions? So the next type of problem is an application going back to triangles. So instead of having the angle, like the previous problems did, we now know what the value of an angle is equal to. So the sine of angle A is equal to 4/5, and that angle is between pi over 2 and pi. So that means it's in the second quadrant if it's between pi over 2 and pi. So I don't know what angle A is, but I know that the sine of that angle is equal to 4 over 5. And then they also tell us that the sine of angle B is equal to -2 over root 5, or simplified 2 square roots of 5 over 5. And angle B is between pi and 3 pi over 2, which is actually in the third quadrant. So when you have a value that sine, cosine, tangent is equal to, and it's not on the unit circle. So again, this number 4 over 5 is not a number that sine is equal to in the unit circle. Sine is 1/2, it's the square root of 3 over 2, it's the square root of 2 over 2, or 1 or a 0. Those are the only values for sine. So when it's not on the unit circle, the only other option that you have is to make a triangle. So I'm actually going to make two separate ones just so that my diagram doesn't get sloppy. I'm going to make a triangle for angle A, and I'm going to make a triangle for angle B. Because if you can't use the unit circle, the other option would be to try and draw a triangle and see if you can use the triangle to answer the question. So it's kind of like one or the other. Can I use the unit circle? If not, we have to go back to making triangles. So for angle A, it's in quadrant 2. So I'll make a diagram in quadrant 2. And we know that the sine of angle A, or alpha, is 4 over 5. So Ingrid, how would we label the triangle based off the sine of angle A being 4/5?
You would know that y value would be 4, and not a minus the sine.
And then the base, the x value would be 3. Since we're on the negative x-axis, it would be a -3. So my one side of the triangle you're able to find either using Pythagorean theorem or noticing that it's a 3, 4, 5 triangle. So that would be my alpha triangle and my triangle A. Going to the second one, This one's in the third quadrant because of the restriction that they give us. So it says between pi and 3 pi over 2. That means it's the third quadrant. So we're going to make a triangle in the third quadrant. So this is my B triangle. And I'm actually going to use the unrationalized form instead of the rationalized value. And that way you can just quickly assign values to your triangle. So I'm going to use the 2 and the negative square root of 5. So Ingrid said the 2 would be the vertical side for the other one, so it's going to be the same thing. That's going to get the negative because you're going down, negative y. And then root 5 would be the hypotenuse because it's the opposite of the hypotenuse. So see if you can find the horizontal or the base, the x value of the triangle using Pythagorean theorem. And then after we do that, we're going to see if we can go back to the formula and try and plug it into the formula to actually answer the question. So this is the work that we need to answer the sine of A plus B. Megan, do you know what the x value is? What? And is it positive or negative? Negative, yeah. So it's a negative 1. Again, we're on the negative x-axis. We're down below on the negative y-axis, so that's a negative 1. Questions so far? So our goal is to then use the two triangles that we have here to answer the question, which would be to find the sine of A plus the sine of B. So we're going to use the pictures. And if you don't like the alpha and beta, make them an A and a B, make them an x and a y. Just use two variables there. So those variables are interchangeable as long as you've got two different values to represent two different angles. So the sum formula for sine says we're taking the sine of the first angle times the sine of the second, cosine of the second angle. You're adding that to the sine of the first, second, cosine of the first. And then you're going to look at the triangle, plug in the information that you have or that you know, and then use the triangle to find the other information. So we know the sine of angle A because we were given that as 4 over 5. So I'm going to take that out and replace it with the value that it's equal to. The cosine of angle B, we don't know, but we have a picture now that we can use to help us find that value. Make sure you're using the right triangle. So angle B would be the second triangle that we drew here. The cosine would be a negative 1 over the square root of 5. And then the sine of B we were given as negative 2 over the square root of 5. And now the cosine of A, we can look over there and we have a negative 3 over 5. So see if you can simplify that, multiplying across for each term and then try and simplify it. So I did my multiplying. What else could we do to simplify it? Yeah?
Rationalize the denominator.
So we can rationalize the denominator. Before you rationalize it, Anna, what do you notice about the denominators?
You can put them like together.
Yeah, these are actually like terms. The denominator is the same, and I'd say add them together first before you rationalize it. Save the rationalizing to the end if you can. So Anna, if we add them, you get
2 over 5 times the square root of 5.
right, and then when you rationalize that, what does that become?
2 times the square root of 5 over 25.
Does anyone have questions so far? So that's creating two triangles, which we've done, making sure they're in the correct quadrant, and then you're finding the sine or cosine, or if we were using the tangent, we would be finding the tangent. of the diagrams that we already have. So again, you're just plugging numbers into the formula.
Why in this one did we add them together when in the ones before this we didn't? Like, for the, like example one, like A, B.
So for example 1, we had the sine of 45 degrees plus.
Like, why did you take the 1/4 out of the bottom instead of just combining them?
Oh, because that's a good question. These square roots you cannot combine because they're different square roots.
Okay.
So I can't make that the square root of 8. If it said 2 square roots of 6 plus 4 square roots of 6, if both of the square roots were the same, then we can add the 2 and the 4 and get 6 square roots of 6.
Okay.
So we could not add these because they're not the same square root. However, this one has the exact same denominator. They're exactly the same square root. So because they're identical, we are allowed to add them together. Really good question. Any other questions? So on the next page, I think there are just 2 other problems, just to kind of see other types of things that you can do with the sum and difference formula. So this is considered an expanded formula because you have the formula already written out for you, whereas the other ones are condensed. So I have like the sine of angle A plus the sine of angle B. Here, the formula is in its expanded form. So I want you to find the exact value of this expanded form. We have the sine of 42 times the cosine of 12. You're subtracting the cosine of 42 times the sine of 12. Essentially, all you need to do is match this up with the formula that it goes with. So if you look at the 4 formulas for sine versus cosine, because it's going to be one of those since it has sine and cosine in it, see if you can match it up with one of the formulas. So look at the way it's written, match it up with one of the formulas for the sum or difference. So Austin, what formula does this look similar to? Right. Good. So alpha would be 42 degrees and the beta is the 12 degrees. So it is in the same form. Yes, this back one is flipped, but multiplication is commutative. I could take cosine of 42 times the sine of 12, or we could write the sine of 12 times the cosine of 42. They can be written in either order. So if I want to find the exact value, now that we know that it identifies or matches to this formula, literally, you're just going to plug in whatever your alpha angle is. That's 42 degrees. You're going to subtract the beta or the B angle, which is 12, and that gives us the sine of 30. And what is the sine of 30, Matt? 1/2. So look at the formula. I think you have like 4 questions like this in your homework, maybe 5. You're going to identify the formula, plug it into the condensed form because you've got the expanded form, and then evaluate it. So this is an angle in the unit circle. The sine of 30 degrees is 12, 1/2. Questions? So that one was definitely not as involved.
So you know that 42 is the alpha because it's, like the first one.
Correct, it's the first one, yes. Yep. Other questions? So the last one is an equation, which looks really crazy up here. Very skewed. We have the sine of pi over x plus pi over 4, and then the sine of x minus pi over 4. And then that's equal to -1. So we've worked a lot with equations. We're going to continue to work with equations with all of the formulas as well. So we're going to be able to pretty much solve any trig equation, no matter how it's written, either by using an identity or by trying to apply a formula to it. So we have the sine of the sum of 2 angles. You're adding that to the sine of the difference of 2 angles, and that's supposed to be equal to -1. Our end goal is to find x. Like anytime you're solving an equation, your goal is to find x. So see, like, what would you think you could try and do here to get x, to try and solve for x, to try and do something with the way it's written? So So is there a formula that you can use or an identity that you can use to start us like rewriting or changing the way the problem's written? Natalie?
Would you try and think of like what on the unit circle, like what sign on the unit circle equals -1?
Not yet, because we need to break it all the way down so that we just have a sign left to equal -1. So that'll be our last step. Ingrid?
Can we use the formulas to put those in the sign?
Yeah, so this here is your sine of alpha plus beta. Bless you. So remember, sine doesn't distribute through, that's a sum formula. So we're going to see if we can change this, and maybe writing it with the sum formula, at least that gets the sign separate from the parentheses, it eliminates parentheses from the problem. So the sum formula for sine says take the sine of the first angle times the cosine of the second angle. So I'm taking the sine of my first angle, cosine of the second angle. And then you're adding that to the sine of the second angle, cosine of the first. So that's the sum formula for sine. If you need to flip the page, it's in that box. Or I would say keep that identities formula sheet handy. Keep that on your desk. It might be handy to use. And then doing the same thing, here's the difference formula for sine. So now let's use the difference formula. So I have a plus sign here. The difference formula says pretty much the same thing, except it's a minus sign instead of a plus sign. So we're taking the sine of the first angle, the cosine of the second angle, and then you're subtracting the sine of the second and the cosine of the first. And that is equal to -1. So it's huge because we've just used two large formulas and we wrote them in expanded form. How can this be condensed or simplified? I know it's a lot to look at. Ingrid?
The sine of pi over 4x or cosine x and the negative cancel, then we have 2 of the sine
Yeah.
x.
So the second term and the fourth term here are opposites. You have a positive and a negative of the same thing, so they cancel. So we'll wipe them out because they're gone. Positive, negative, same term. The other two terms are also identical to each other, so we have 2 of them then. Just like if I had an x plus an x, I would make a 2x. So if they're the same, we can add them together by making 2 of them. So our huge problem has definitely condensed. 2 things canceled, 2 terms were able to combine together. And now we're getting closer to having that x by itself. So what else can we do to try and evaluate or simplify this? Maddie?
Divide by 2.
So we could take the 2 to the other side, divide by 2. So then we would have the sine of x cosine of pi over 4 equals -1/2. Is there anything else we could still do? Megan?
You can change the cosine of pi over 4 into the square root of 2.
Yeah, we actually know what this value is on the unit circle. So that doesn't have an x with it. That means you can evaluate that. So we still have the sine of x. And you said the cosine of pi over 4 is?
The square root of 2.
Square root of 2 over 2. I'm just going to put that in front because it's a number. So a number generally gets written in front. Instead of writing it in back. So we're really close to having sine by itself. Very close. Natalie, what's left that we could do to get sine by itself?
Divide the square root of 2 over 2.
Instead of dividing, yes, dividing is not.
Multiply by the reciprocal.
Yeah, let's multiply by the reciprocal. So dividing isn't wrong, but because we're dealing with fractions, if we multiply by the reciprocal. So now I have sine by itself, which is our goal, to get that one function with an x by itself. And Natalie, when you multiply, what do these give you over here?
Would it be just negative square root of 2?
You're so close. Those cancel. What's on the top if I go across?
The negative 1.
-1, and the bottom is the square root of 2.
So it's the square root of 2 over 2.
Perfect, there you go. So now I have the sine x equaling negative square root of 2 over 2. So So we got terms to cancel, we were able to combine terms together. We could evaluate one of the functions because we actually know what the cosine of pi over 4 is. And now the last thing we have is the sine of x equals negative square root of 2 over 2. With a trig function, your goal is to find x. What is x in a trig function? What kind of value is x? That's the angle. So now we've done the solving equation stuff. We want to find the angle. When the sine is equal to negative square root of 2 over 2, and remember there are two of them, because sine is negative in 3 and it's negative in 4. So all of this stuff we've been doing with solving the equations, now I have the equation that we have to finish solving. We have to find the angle. Does anybody know when the sine is negative square root of 2 over 2 in the third or the fourth quadrant?
3 pi over 4 and 7 pi over 4.
So 3 pi over 4, you're so close.
Oh.
I agree with 7.
5.
Yeah.
So.
That's good. 5 pi over 4 and 7 pi over 4. Questions? So the part that makes this chapter so hard is, the fact that you have a ton of identities and formulas, but it also requires a lot of memorization of the unit circle and pulling that back in. The stuff that we did in chapter 4 is now coming back. And we're going to continue with other formulas as well. Are there questions that you have with the sum and difference? In most cases, it really is like plugging and chugging through the formula. Even here, we tried to use the formula, apply it, but then we got things to kind of reduce and cancel out for us. So the homework you have in the book, the problems that are like 31, 33, 35, those problems are where you have the expanded form and you're going to condense it. I think the last three problems, 77, 81, 85, are the equations that are like this. And then the first couple are just trying to use the formula, getting an exact angle. And then I believe there's a couple where you're creating triangles. So I think like 49, 53, 55, you're making those two triangles and you're applying the triangles to the formula. So you have a couple of questions on each concept that we looked at on each of the 4 examples. So saying that, I have 19 and 55. Anybody interested besides Anna? No offense to Anna. Megan and Jordan? Megan, would you like 19 and Jordan 55?